Good morning, dear colleagues. Good morning, Volodymyra. My name is Shatskyi. I'm working at the Institute for Applied Problems in Mechanics and Mathematics of National Academy of Science of Ukraine. In this presentation, I would like to talk about the theoretical modeling of partially healing of surface crack-like defects in solid bodies. Modern technologies for healing defects are a productive means of extending the life of structures of long-term use. Such operations are often used in various industries, but they strengthen new pairs of machines and structures during their manufacture, and to restore worn working surfaces with acquired defects. However, in cases of partial restoration of the integrity of bodies, the problem of sessions of significant concentration of stresses on the banks of defects and determining the ultimate strength for the composition obtained as a result of restoration remains relevant. Methods of calculating the residual service life of pairs with defects handled by injection technologies are discussed, for example, by Panasiuk, Sopron, and co-authors. This publication focus on limit state evolution of structures with defects filed with low modulus materials. The purpose of our paper is to develop an engineering methodology for evaluating the effectiveness of restoration of elastic bodies with surface defects. In the course of the study, the previously proposed approach to estimating the limit equilibrium of bodies with cracked, partially filed with non-contrast material is developed. Problems of a non-contrast interface were also considered by Gao et al. Model of partially headed crack. A crack in a deformed body is understood as a displacement discontinuous surface omega 0. As a result of the restoration of the integrity of the body in some domain omega healing, we get a new object, a partially healed cracks with a discontinuity of movements on the surface omega equals omega 0 minus omega healing. This domain can be generally multi-connected. For simplification, we adopted the following hypotheses. The first, the elastic properties of body with a headed crack are preserved. It means the details of the rheology of the connected layer are neglected. The second hypothesis. The specific surface energy of separation of surfaces of fracture toughness of the material is in the headed area is generally different from the corresponding values in a solid body. Thus, we came to the problem of mechanics of crack omega in a semi-infinity body, homogeneous in terms of elastic properties and heterogeneous in terms of crack resistance. Okay. Moment. The degree of crack healing was described by two parameters. The ratio of crack resistance of the body and aggregate materials, eta, which characterizes the quality of the process of healing, as well as the ratio of the areas of the healed domain and the initial crack. This parameter describes the quantitative degree of recovery. The efficiency of healing was solved as a ratio of the limit values of the load for the healed and primary cracks. Okay. We started from the case of single surface crack. This is the assumption of the plane problem of the theory of elasticity. We consider a half plane with edge cracks of normal separation of length L0. We will alternately analyze two options for crack headings near the tip of defects and near the edge of the half plane. Position A is the starting, means the starting configuration. Positions B are the represent the partially headed configuration, and positions C represents the model for calculation. In case of healing near the tip, in the starting configuration, stress intensity factor is known. Following the Griffiths criterion, we apply the ultimate load for a half plane with the edge crack. For a shortened crack, length with the length L, we have formula 2. We define the desired healing efficiency for a single crack as the ratio of limit loads 2 and 1. Equation 3. Here parameter eta describes the quality of healing, parameter psi describes the quantitative effect of healing. There is the analytical result. In the case of healing near the edge of the health plane, we have also analytical results. As a result of healing of the defect to the depth, to the given depth, we have internal cracks of length 2L, located on the segment, this segment as the calculation model. In this case, we have an internal crack. Right? The following relations are obvious. In this case, we can obtain the stress intensity factors, where F1 are known functions obtained by solving of the problem for a health plane with internal section. The limit load will be by formula 4, and by comparing expressions 4 and 8, we finally got the formula for the healing efficiency. Formula 5. The case of periodic series of surface crack. Now, as a starting configuration, we consider a health plane with a periodic system of surface crack located perpendicular to the edge. As before, we consider the fraction model 1. That L0 is the length of unhealed cracks, and there is the distance between them. This is a period of location. The stress intensity factor and ultimate load for this problem depend on the dimensionless parameter omega. L0 divide D. Repeating the previously discussed algorithm, we found results for a periodic ensemble of partially healed defects. In particular, in the case of treatment of peaks, it's formula 7. In the case of treatment of the edge of the health plane, it's formula 8. Here, F2 and F2 and F3 are known functions that characterize the dependency of stress intensity factor on the mutual location of surface and internal cracks, respectively. Results and discussion. The results of calculation of the healing efficiency for different values of parameters eta and omega are presented in the figures 3 and 4. Only values in horizontal axis, we have the parameter psi. It's degree of the quantitative degree of the field of cracks. Vertical axis is efficiency of helium. Parameter eta is fixed. Parameter omega have fixed values too. The case of omega equals null, 0, means the single defect. As can be seen from the above graphs, an increase in the degree of treatment C always contributes to the success of the restorative operation, especially since the quality eta is higher. When increasing the parameter omega for a periodic structure, the efficiency he always decreases. Why? The reason for this phenomenon is the competition between the shortening of cracks and the weakening of the shielding effects of the interaction of parallel defects. Finally, comparison of these figures shows that no contrast healing of surface crack near the edge of the body is generally more effective than healing near the tips of the defects. Conclusions. The paper developed a model of crack healing with a non-contrast material in bodies with surface defects. In analytical and numerical form, quantitative estimates of healing efficiency are established depending on 3 parameters: degree of filling of cracks, cracks resistance of the newly formed interface, and mutual location of cracks. Body restoration, we observed then body restoration near the surface is shown to be generally a better solution than headed near the defects vertices.
Thank you, Professor.
It's finished. Thank you very much for your attention.